Well, good morning. This is Wednesday morning, the 22nd of March, 9:35. A little late getting started, but I've been waiting for students to show up. But I need to quit waiting and get on with class. This is supposed to be Cal 1, Math 125, and no one else is in the room but me. So, where we left off last time, we were in Chapter 3, Differentiation, a really long and involved chapter, in Section 3.8, Implicit Differentiation, and we had just finished, or had almost finished, Example 2. Now, let's go back and figure out what we've done so far in Example 2. This was the theorem. We're really not using that much, but I'm trying to find where we are here anyway. Oh, sorry. I forgot. We're in a different section. We're in 3.8. However, I believe that's 3.9 on the slide set. Let me see. They've got the slides. This is one difference between the two editions of the book. I don't think this is it either. So let's go to 310. Sorry, I should have caught this earlier. I don't believe that's it either. I can't tell. I don't believe so. Let's try 311. Nope, that's not it either. Is it 3.7? I know we had the slides. Let me expand this to see. I don't think that's right. No, definitely not that one. Okay, I'm losing my mind here. Implicit. Let me go get the other book, see what section number it is. Okay, section 310. Sorry, I should have had this already. Sorry about this. Okay, yeah, it was too small to see. Let me see. We don't want that one. Okay. We don't want this one. We don't want that one. We don't want that one. Okay, this is the one we want. Sorry about that. Okay, this one will go to current slide. why I'm not seeing, I guess we worked off this slide the whole time. Okay. Yeah, this was the example. Okay. No wonder I couldn't see it. You can't read it. Y to the fourth plus xy is equal to x squared minus x plus 2. We did the implicit differentiation. It says find the equation of the tangent line at the point P11 on the curve, this curve. Okay. Now, we'll see the picture of the curve later. I think we looked at it before. But anyway, we found out the point P11 was on the curve. We checked that. We next needed to find the derivative at 1, and that's what we did last time and found out. And of course, I'll need to shrink it and get my pen set up. Okay, and we found out that y prime at 1 is equal to 1 over 5. Okay, now, so what we now have is the point 1 that's on the curve. We have the slope at that point 1. So now we need an equation. Well, that's not too awfully bad to do, because basically it's our point slope formula. Y minus y1 is equal to m times x minus x1. Okay? Remember, the x and y are your variables, your y1, x1, that's your point 1. Okay? So this will be y minus 1 is equal to 1/5 x minus 1, because both of those are 1s. Okay? So that would be y minus 1 is equal to 1/5 x minus 1/5. Well, let's add 1 to both sides, but on this side I'm going to add it as 5 over 5, because that's what 1 is, and that's going to make it easier to add. These add to 0, so y is equal to 1/5 x plus 4/5. And that's the equation of the tangent line that you see at the bottom of, or near the bottom of page 168. Yeah. I'm going to have to turn on the light. It's just a little too dark in this corner. There's no class. The students are in the room. They'll have the projector on, and I don't have the other lights on, but I need it. This print is too small. All right, here's the conceptual insight that follows that. The graph of an equation does not always define a function, because there may be more than one y value for a given value of x's. Implicit differentiation works because the graph is generally made up of several pieces called branches, and each piece, which does not define a function, and this is done later in advanced calculus, implicit function theorem. For example, the branches of a unit circle, y is equal to square root of 1 minus x squared, or negative square root of 1 minus x squared. Similarly, the graph of figure 3, and that's what we're going to go to next, this one, there's the tangent line that we just did. Okay. That's the graph of the function with its tangent line at point 1. And if you were to try to deal with that, you could break the branch. Sounds strange, doesn't it? At the one point that is the farthest extreme here, okay? At the point where, right about there. Now, of course, if I actually try to draw it, it's going to shrink, and that's not too bad. Right there. So your upper branch is here, your lower branch there. Both of those are now functions, because it doesn't back up on itself from that point. If you get the extreme left value of there, it doesn't back up. Now, that won't work with every graph, but on this one it certainly does. Okay? I think we're ready now to go to example 3. Oh, this is that circle they were talking about under the conceptual insight. Oh, no, sorry about this. I'm not at the place in it. This is a slide we've already done. Okay. Okay. Sorry, we were beyond this. That was the other thing. I couldn't find where we left off here. Yeah, there's what we were just looking at. That's that one. There's the graph of the function. Then you pick the extreme left value as your starting point, and you can go the upper branch or the lower branch from there. Okay, here we are at example 3. Oh, that took a while. Find the slope of the tangent line at the point P11 on the graph of this one. Different function here. E to the x minus y is equal to 2x squared minus y squared. Okay? We want the slope of the tangent line. They didn't ask for the tangent line this time, just the slope of it. Okay? Now, definitely this is not one you can solve for y. Any way, shape, or form that I can imagine could you get this explicitly solved for y. So therefore, what do we need to do? Our implicit differentiation going for dy dx. Okay? So, let's take the derivative of this side with respect to x, and then we'll do the derivative of this side with respect to x. Okay? So what's the derivative of e to the x minus y? The derivative of any exponential function is itself e to the x minus y. Okay? Then chain rule it times the derivative of what's inside. I'll write it this way, d by dx of x minus y. Chain rule. Okay? We'll go on and do the first part of the next, of the right-hand side too. Derivative of that would be for x, and derivative of that with respect to x would be minus 2y times dy dx, which I'm just going to write y prime if that's okay. Okay, let's go back here. We had e to the x minus y times derivative of this thing. Well, that derivative would be 1 minus y prime, right? Is equal to 4x minus 2y prime. Okay, now if you remember what we did before, we need to isolate the y prime. Okay, which first means get it on the same side, but even before that, we've got to sort of mess it up a little bit here. This is e to the x minus y times 1 minus e to the x minus y times y prime. Okay? That's equal to 4x minus 2y prime. Okay. Need to get the y prime terms on one side or the other. Now, I personally don't have a preference. Not going to make a lot of difference which way you go. So, let me just look and see which way the book went, so I'll go the same way. Yeah, they added 2y prime to both sides and subtracted e to the x minus y, because that didn't have a y prime in it. Okay, these go out, those go out. Okay, go back up to the top, and we have 2y minus e x minus y times y prime. That's combining these two together. 2y minus e to the x minus y times y prime is equal to 4x minus e to the x minus y. Well, let's divide both sides by 2y minus e to the x minus y. Okay, and there's your answer. y prime is equal to 4x minus e to the x minus y over 2y minus e to the x minus y. Okay. Now, even though we got the picture of the graph in front of us, I don't trust it, do you? Okay. Let's make sure that point P11 is indeed on our original equation. So let's do it. E to the 1 minus 1 is e to the 0, that's 1. Okay, is that equal to 2 times 1 squared would be 2, minus 1 squared would be 1. Sure enough, that is 1. So 1, 1 is on that curve. Okay? At least some part of that curve. Okay? Now, what we do now, since we probably should have done that at the very beginning, we now want to know what the slope was at that point. So here's y prime at any point. So the y prime at the point 1, 1 would then be 4 minus e to the 1 minus 1 would be 0, so it would be e to the 0 is 1, so that would be 1 over 2 minus 1, and that would be 3. There's your slope at that point, and that's exactly what they got. Good deal. All right, now if that wasn't a weird enough looking and operating problem, let's look at example 4. Whoa. Here is calculate dy dt at point P at the point 0, 5 halves pi on the curve of y times cosine of y plus t squared is equal to t cubed. Okay. There is the form, okay? And we're to calculate dy dt of that at the point 0, 5 halves pi. Well, this time let's start at the beginning. When, okay, independent variable is t, so t equals 0, and the dependent variable is y, and that's 5 halves pi. So let's see if indeed we get this. This would be 5 halves pi times the cosine of 5 halves pi plus 0. Okay, so 5 halves pi. Supposedly that's equal to 0. Let's see if it is. 5 halves pi times the cosine. Okay, let's think about your cosine function. The cosine function is always a maximum at 0 plus or minus 2 pi, a minimum at, which would be a negative 1, at pi plus or minus 2 pi, and it's 0 in between those, which is all the half pi's. So cosine of 5 halves pi, just like cosine of 3 halves pi, like cosine of 1 half pi, which is cosine of, yeah, all those are 0. So sure enough, this just checked. Okay, the function is does touch that point 0, 5 halves. Okay, so let's erase. I think we'll erase all that. All right. So the next thing we've got to do, we want to calculate the dy dt at that point P, 0, 5 halves pi, okay, on this curve. I think I'm going to write this, excuse me, a little bit bigger. Y times cosine of y plus t squared is equal to t cubed. That's the equation that we're trying to deal with. Definitely not a function. If you look at that curve there, not a function. Okay? But what we want is calculate dy dt at this point. We want dy dt at the point p equal 0, 5 has pi. Yeah. Okay. If we're looking for dy dt, that sort of indicates we need to take a derivative with respect to t. What you start off with here is a product rule. Okay? So, I don't know which way you like to start. I think I'll start with y prime times that. So that would be y prime times the cosine of y plus t squared. Okay? Plus, product rule, y, and what is the derivative of cosine but minus sine? So this becomes a minus, it's y times a minus sine of y plus t squared. I did write that right, wasn't it? Yeah. Okay. But now you got a chain rule to do. You got to do dy, derivative of this thing with respect to t. So I think I'll write that down just so you'll see what I'm doing. D with respect to t of y plus t squared. Okay? So it'll be derivative of the first term, y prime, times the second function, cosine blah, 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 plus the first function, y, times derivative of the second. Second outer function is a cosine. Take the derivative of that, you get minus sine. That's where the minus sign showed up here. Of sine of that thing at that. Then times chain rule, the derivative of what's inside there. And we'll do that in the next step. Let's go on and do d by dt of t cubed. That would be 3t squared. We know what the right-hand side is. So this gives us a y prime times the cosine of y plus t squared minus y times the sine of y plus t squared. Now, derivative of that part. Okay? This will be a y prime plus 1 plus 2t. That's equal to 3t squared. Okay. I don't know why this happens about this time of morning. It did, I think, yesterday too. I can't remember, but it has sometime this week. I don't know if the temperature changing. I don't know if the ventilation's coming up. I don't know what, but suddenly I'm getting completely but congested in such a way it's hard to breathe. All right. Now, here is our big, ugly, hairy derivative. Okay? Now, what we're going to wind up doing at some point is solving for y prime. We have all the ingredients here. It's just really messy. Okay? So, but since we have all the ingredients and everything's in place, we can go on and plug in the values where we're interested in the derivative. I don't really care where it is anywhere else. I won't know the derivative there. So, this is my t, this is my y. Okay? So let's plug those values in. Y prime, that's what we're looking for. So, don't hang on to that. Times the cosine of, and your y is 5 pi over 2 plus 0 squared. So that'll just be that. Minus y, and the y is 5 pi over 2 times the sine of, sorry, hard to breathe, 5 pi over 2 plus 0 plus 0. So we'll just leave that alone. Okay. Times, here's the y prime again. That's what we're ultimately going to be solving for. Plus 1 plus 0. 2 times 0 is 0. So we really don't need that last plus. Okay. And this is equal to 0 because t is equal to 0. That simplifies things considerably. Okay, so let's again multiply through here. We get y prime times the cos. Well, wait. Let's hold on a minute. Okay, what is cosine of pi halves? We've already been through that, right? That's 0. Yo. So if cosine of pi halves is 0, but what is sine of pi halves? Okay. Now, I don't know, 5 pi halves, sorry. Let's do the graph of a sine. Okay. Starts at 0, and at pi halves, that's the ugly pi, it's at plus 1, then it's 0 again at pi, then it's minus 1 at 3 halves pi, okay, I don't know where my line is, there's 1, there's minus 1, so that's down here somewhere, and then at 2 pi we're back here again, made one complete cycle, can't do it, something like that. Well, the next point here would be 5 as pi. That's the one we're interested in, and the sine of 5 has pi, sure enough, is plus 1. So this will be 0 for that term. This will be minus 5 times pi halves. Sorry, wait. I think, I hate to stop this soon into the class. I think I've got to go get something, at least a drink of water or something, to try to loosen my head. I'm just all clogged up. So hold on just a moment. All right, sorry. I just had to go clear my head some. It isn't completely clear, but at least I can breathe a little bit better than I could earlier. All right. Where we were here, we had y prime times the cosine of 5 halves pi. We've already talked about that. That's 0. Cosine is 0 at all the half pi's. So that part is 0. Minus 5 halves pi times the sine of 5 halves pi, where we just saw here, that's plus 1 there. So that's minus 5 halves pi times y prime plus 1. And that's equal to 0. That's a lot simpler equation than what we had before. Now, to clean this up just a little bit, let's write that as minus 5 halves pi times y prime minus 5 pi over 2 is equal to 0. Add the 5 halves pi to both sides. Okay, wipes that out, and then you have minus 5 halves pi y prime is equal to 5 halves pi. Well, guess what? Divide this away and you get minus 1. Y prime is equal to negative 1. That's all they asked for. So you have to take derivatives. You have to carry all that out. You can do all the steps. But when you've got it all out there, rather than solving for y prime and then plugging in the values, since you got it all there now, plug in the values first and then solve for it, especially when there's a bunch of zeros in there and you can get things to work out as easily as this one did. Okay, so that was example 4. They didn't want me to graph it, thank you very much, but neither did they ask for it at any other place. Other places would have really been a bear, okay? That t's equal to 0 wiped out a lot of terms. Cosine of pi halves equals 0. That wiped out at least one term, okay? Everything got a lot simpler. All right, then we move to derivatives of inverse trigonometric functions. Well, wait, okay, sorry about this. Here's the steps that we did. Let's see how they did it. The derivative of y times cosine of y plus t squared is equal to derivative with respect to t of t cubed. And the product rule, again, this is maybe a little neater than my writing, but it's the same thing. This is a product of two functions, y times the cosine function. So take the derivative of the first, y prime, times the cosine, just like it sits. And then it's normally a plus y times derivative of cosine, but derivative of cosine is minus sine of all that. But then you've got the derivative of what's on the inside, chain rule, and that gives you y prime plus 1 plus 2t. Okay? And derivative on the other side is 2t squared. Okay? Now, that's your differentiation. Everything you need. At that point, you plug in t equals 0, y is equal to 5 halves pi. And when you do that, you'll come up with the answer. Now, that's all they put in this section. Okay? They don't do derivatives of inverse trigonometric functions here. That must be showing up somewhere else. I think that may have been back in the section we just went from. Okay? So I think that's what this new edition has done, that combined two sections. Okay? And I think we looked at these already, and I think we've done just about the rest of this section here. So well, we may not have done all the examples, but frankly, basically when I'm doing these, I don't try to memorize these. I look them up, okay? Because in memorizing, have I got the sign in the right place, or is the square root here or not there? So I think we did all those before, so we're just going to move right on past those, and that's going to end our 3.8. Okay, if y'all were here, I'd ask if you want to do preliminary questions. Since you aren't, I'll say do those on your own. Okay, if you have a problem with any of them, please bring them to class Monday after spring break. I guess all of you realize next week is spring break week, so good news, bad news situation. The good news is it's spring break. The bad news is we won't be meeting for Calculus 1 until the following Monday. So not next Monday, but the following Monday. If you have any questions on these preliminary exercises in 3.1, preliminary questions in 3.8 exercise, please bring those and we'll do those. Otherwise, homework exercises here, do 1. Do any of the odds 3 through 7. Do any of the odds 9 through 25. Do either 27 or 29 or both. Now those are the inverse functions. Again, the formulas are at the top of the page. You can use them right there. And then any of the odds 31 to 43. then I would suggest you doing any of the odds 45 to 49. Do 51. Do any of the odds 53 to 59. And then do any of the odds 61. Wow. They just keep on going, don't they? 61 through 75. Now, you don't have to do a lot of those. I would do at least one, maybe more. Take a look, see if you can figure out. But I wanted to point out on question number 66 that you don't have to do. Here is a folium of Descartes. It's a cubic function that was studied by and first discussed by the French philosopher mathematician René Descartes. Okay, folio meaning a leaf or a page type thing, folio. Okay, his scientific colleague Gilles de Roberval called it the jasmine flower. And both men believed incorrectly that the leaf shape in the first quadrant was repeated in each quadrant. However, it's not. Okay, so you can certainly write on Descartes. You could certainly write on de Roberval. Okay, must have been a science mathematician. Okay, you can write on the folium of Descartes, especially if you can find any application to it. You know, maybe an interesting search there. Or what did they discover about it? Where did they go wrong? You can think of several things. Up to you. All right, let's continue. Then do either 77 or 79 or both. And then do either 81 or 83 or both. And then the rest of these are for further insights and challenges. I'll let you determine. And there's another name in number 86, Jacob Bernoulli. He's certainly a good paper topic. The Bernoulli family would be a good paper topic. They're an interesting group of people, brilliant scientists and mathematicians, engineers, probably some too. The one they're talking about there is a lemniscate curve by Jacob Bernoulli. I'll let you decide if you can find anything special on that. I'm not suggesting there is anything, but if you're interested in it, go for it. All right. That ends what we're going to do in 3.8. So where we go from here is 3.9. But that was just 3.10 on the slide set. Now I've got to find where 3.9 is on the slide set. I'm guessing that's 3.11. Let me see if that's indeed the case. PowerPoint is really, really, really slow. I can't see that yet. Let me blow it up. And no, that's related rates. Okay, so we'll get out of that. And sorry about this. Let's try 3.9. It'll be amazing if it's the right numbering. Yes, I think this is it. Okay. 3.8 was 3.10, but 3.9 is 3.9. Go figure. Okay. Now, back in section 3.2, we proved that for any base, or at least we talked about, for any base greater than 0, positive base, d by dx of b to the x, let's write this down again. Whoops, let me get my pen back in the dark color. D by dx of b to the x, this is all your b's are positive here, is equal to some coefficient function, m of b. I kind of don't like that way they named it, but it's fine, times b to the x. Okay? It's some coefficient function of b times b to the x. What is that m of b? The m of b is equal to the limit, this is what we were doing back then, as h goes to 0 of b to the h minus 1 over h. Okay. Man, I feel it clogging up again. This is aggravating. If we look at that, we see that b to the h is approaching 0. B to the 0 would be 1. Your numerator would be approaching 1 minus 1. The denominator is approaching 0. 0 over 0. Definitely an indeterminate form. That's what that coefficient of b, that coefficient function of b, m of b, would be. Okay. Now, but we were not able to identify what that factor is other than that to say e is the unique number for which m of e is equal to 1. That's what we said back before. What we're going to do now is use the implicit differentiation we just did to prove that m of b is equal to log b, natural log of b. Okay? So how we're going to do this is, let's let y equal, oh, thank you for coming. Goodness gracious, I've been so. What's that? Oh, I see. Yeah, I've noticed in several classes it looked like instructors use this last day of a Monday, Wednesday class before spring break to give tests.
Well, my class is on the Birmingham, so I still get to come here.
Yeah. All right. Let me go back and mark Nicole here. The rest of them are not. First, turn on this. So you're going to need to listen to on YouTube for the first part of the class because we did go over, I went over stuff and also did some homework assignment on it. So hopefully you'll be able to follow it. When you do hear it, I had to stop at least once. I was starting to wonder if I was going to have to start again. My head, I don't know if the air kicks in or something. It's just, yeah, and it could be that. And I think I may have told you last weekend, I was working in the yard all day Saturday and messing with pine straw, and it had, you could see mold and stuff in it. I didn't notice anything then, but boy, this week I've sure noticed stuff. And so my head is somewhat clogged up, and like you said, it could be the pollen issue.
I take the shots.
Take what?
I take the shots.
Science medicine, is that what you said?
I take the allergy shots.
Oh, I see. Okay. Yeah. Well, yeah. I hope I don't have to, but maybe as I get older, I'm going to have to get on something like that. All right, we're right at the beginning of 3.9, which, now I don't know if you remember from last time, 3.8 in our text was 3.10 on the slide set, so I wasted time trying to remember where that was then. So then I went looking for 3.9, and sure enough, it is 3.9. But I can see one advantage of why they may have rearranged it for the new edition. But the slide set is from the old edition. All right, what we were doing here, we're introducing a function here. This goes back to what we had before. Y is equal to b to the x. Okay? What our goal is to find dy dx. Okay? Now, how you go about doing that, we don't have a rule yet. We will, but we don't have a rule yet for what to do with that. So here's what they do. What undoes an exponential? This, oh, by the way, this is on page 175, section 3.9, chapter 3. What is the inverse function of an exponential? A log, exactly. So what we're going to do to undo this exponential on the right, we take the log of both sides. So that'll be the log of y then is equal to the log, natural log of b to the x. Now I don't know if you remember the properties and rules for taking logs and things like this, but if you have a log of something raised to a power, you can bring the power outside the log. That's the same as x times the log of b. Okay? Now, if we're looking for dy dx, now we can take, and we're basically going to eliminate that step. We're going to go just between these two. Let's do dy dx. So derivative of log is what? You remember it?
Natural log.
Yeah. Derivative of a natural log. Log y. What's the derivative of natural log of y? 1 over y. And then chain rule it times y prime. This is implicit differentiation like we did in the last section. And that's equal to, and here, now log b is just a number. It's just a constant. So that's just going to be log b. Okay? And now we're really close. Multiply both sides of the equation by y. Get rid of it on this side, and you got y prime is equal to log b times y. Okay? Well, what's your y? Y is b to the x. So this is log b times b to the x. Because that was your y up here. Okay? And that's where we get theorem 1. Derivative of a function, which is a exponential function, f of x is equal to b to the x. Derivative of that function is going to be the log of the base times b to the x. So it looks in one sense a lot like your exponential function, right? It is an exponential function. Derivative of exponential e to the x would just be e to the x. So that part stays almost the same. The only difference is e to the x doesn't have a coefficient in front of it. Well, what if it did? What's the natural log of e? One. No, natural log of e is 1. So that would be 1. So, yeah, this reduces to derivative of e to the x would be e to the x. But if it's b to the x, then you have a coefficient in front, which is log b. Now, this is only good for b greater than 0. Now, it's a pretty obvious reason why we had to have only positive b's, besides the fact that taking a negative base and raising it to powers is a really ugly thing to do. But here you see it has to be this because the log of a negative number is not defined. The log of 0 is not defined. So you have to have b being positive, strictly positive, not even 0. Okay. So there's where we begin. Let's do a little example with that. What is 10 to the x? That's to the x, not 10x. Okay, let me clean that up a little bit. My superscript didn't super very much. 10 to the x. Okay, if I'm taking the derivative of that with respect to x, what would that be? By this rule here. by this rule here, the b is 10. So this would be log 10, natural log of 10, times 10 to the x. Okay, and of course, 10 is greater than 0, so it fits. Okay, natural log of 10 times 10 to the x. All right, let's go to, in fact, I don't think, not there yet, so let's clear the ink on the slide. Okay. Example 1. Differentiate this. F of x is equal to 4 to the 3x. So what is df dx? Say again? Yeah. If that's your function, 4 to the 3x, and you're trying to get the derivative of that function, it's just like here. Here, the only difference is the b is 4, and instead of x, you have 3x. Well, you start with log of 4, right? Okay, so that's the first part. Natural log of 4, that's your coefficient, you might think of it, times 4 to the 3x, but then you still have to do a chain rule and do the derivative of 3x. And what's the derivative of 3x? 3. And Rodney's here. All right. All right, we're in section 3.9. We finished 3.8 already this morning. We were in that last time, and now we're in 3.9. And this is example 1 in 3.9. Okay? So what we have, our final answer is 3 log 4 times 4 to the 3x. Okay? 3 log 4 times 4 to the 3x. Now they put the 3 inside the parentheses. I put it outside. It doesn't matter. It's just 3 times log 4. Okay. That was the A part. Here's the B part. What is f of x is equal to 5 to the x squared. And we're looking for df dx. What would that be? Now, this is not 5x squared. It's 5 raised to the x squared power. Second? 4x? Okay. Let's take it a step at a time. Let's look down here at our theorem. Okay. Anytime you have derivative of a base raised to a power, first thing is it's the log of that base. What's your base there? 5. So it's log 5. That's how we're going to begin. Natural log of 5. Okay. Times your exponential function. That's going to be 5x to the x squared. Okay. But then we have to chain rule it. Okay. You repeat this there. That's what we did. But now we chain rule that. What's the derivative of x squared? 2x, exactly. So that's what goes, usually we put that in front, 2x, okay? Now there's other ways you could write it. You could write it as x times 2 log 5 times 5 to the x squared, any way you want to. Let's see how they did. They did 2 log 5x, okay. They wrote it, and it's perfectly fine. Our way is just as good. They wrote the numerical part first, 2 log 5. That's just some number, maybe irrational number, but it's just some number, times x times 5 to the x squared. Okay. I don't see that's any clearer, but I sort of see what they're doing. they're getting the coefficient out front, and then the product function here, x in front, and 5 to the x there out there. Okay, that was example 1, parts A and B. Now, next we'll find the derivative of f of x equal log x. We've already done this, haven't we? Okay, but we're doing it again. Okay, now I don't know, maybe we have it in this course, but we did just a little while ago. I asked what's the derivative of log x, and I think I gave the answer, but indeed that was right. But let's do derivative of that. So let's start with, I think I'll clean the page. In fact, I think I'll go to the next page. Okay? We're going to start with this. F of x is equal to the natural log of x. Okay. Now, we're going to start with having, well, you got to have x greater than 0. Why? You can't take the log of 0. It's undefined. You can't take the log of a negative number. It's undefined. No way you can do it. I don't know if you remember this, but the log function is the natural log function is the inverse of the exponential function. And if you drew the exponential function on a graph, it goes to the point 0, 1, and it goes like this. Okay? Now for log to be its inverse, then it would have to go through 1, 0, right? And it would then go like this. And sure enough, those two functions reflect across the identity function. So you see log, this is log, that's exponential here, here's log here. Log is not defined at 0 and is never, ever negative. So that's why you have to have x greater than 0. Not even equal 0, not equal to 0, greater than 0. Okay. So we're starting with that. Now, I don't know if I know Rodney wasn't here, but Nicole was. When we did the last one, when you had an exponential as your function, you took a log to simplify it. Well, now we have a log as a function, so we're going to do an exponential. So let's take the exponential of both sides. E to the f of x is equal to e to the log x. But an exponential and a log function undoes each other, right? So this is, the right-hand side is just going to be x. Okay? Because they're inverse functions of each other. And x is equal to e to the f of x. Goodness gracious. Nicole and I were talking, or I was doing most of the talking. I'm getting all clogged up, and she suggests it's probably the pollen, and she's probably right. But that's almost a little on the gross side, but I don't know why, but last night, and we had seen it a couple times earlier, all of a sudden, I guess with spring coming, the flies are out. And, I mean, we had several buzzing in our house. Karen was saying, where are they coming from? You know, I guess they just hatched, or they're coming from down south. I don't know where, but we just have, our dog hates buzzing flies. I mean, she hates it. She was running around trying to get away from them, getting under our legs and stuff. So Karen said, get a fly swatter and try to go after them. Well, our ceilings aren't quite this tall, but the ceiling in the kitchen is about close to 10 feet, between 9 and 10 feet. We're in an old house. And so the flies were congregating around the light because they want to go to the light. So she said, try to get them. So I had the fly swatter trying to do them. And one of them was on the thing. And I swatted that, you know, it's about this height. It really is, pretty close to this height. And when I hit it, dust came down. We hadn't messed with that light fixture probably in a year and a half or more. Last time I changed the tubes, and I don't even remember when it there came dust down, and I got all in my eyes and maybe breathed some in too, so that may be it too. And so this morning I woke up and I had conjunctivitis in both eyes, and I put medicine on. They're better now, but they're itchy like crazy. So that's maybe another part of why my head is clogging up. So anyway, we've got this, e to the f of x is equal to x, okay? Now, what we're going to do now is differentiate both sides of this. Derivative of this with respect to x times derivative of this with respect to x, okay? Well, derivative of e to the f of x would be, derivative of an exponential function is what? It is exactly it, e to the f of x, and then chain rule that times f prime of x, okay? And derivative of dx by dx is just 1. So now we have f prime of x is equal to, divide both sides, 1 over e to the f of x. But what is e to the f of x? E to the f of x is x. So this is f prime of x is equal to 1 over x. And that's exactly what we get here. So again, it's almost like, feels like you're running in circles, but you really were accomplishing something. So here is your theorem 2. And I've got writing all around it and through it, but hopefully you can still see. Derivative of log x is 1 over x. Now, I'm sorry I asked you that earlier. I didn't realize we hadn't done it yet. But that's what derivative is. Natural log of x is 1 over x. And that, again, is only good for positive x's. Certainly, x can't be 0 for this, but there's nothing that would allow x not to be negative here, except here, log of x can't be, you can't take the natural log of a negative number. So it's not just it's not equal to 0, it has to be greater than 0. Okay. So that's theorem 2. Let's do example 2. And I think we're probably going to have to do that on the same page. I don't think we have. All right. Let's, oops, wrong one. Let's clear all this ink off the slide. And let's do example 2. Differentiate this. Y is equal to x log x. What we want to do is dy dx. Now, we could have just called that y prime if we wanted to. So what are we going to do with that? How are we going to differentiate x log x? What's the first thing you notice about it? Okay, it's a product function, right? So we use the product rule. And how does that go? Derivative of log x over x plus
log x times the derivative of x.
Perfect. Okay. Now, remind me what's the derivative of log x? X times 1 over x plus log x. And what's the derivative of x with respect to x? 1. Yes, exactly 1. So what we have is 1, because x over log x, x over x is 1 plus log x. Huh. That's it. 1 plus log x. Okay? Make sure the book got that. Yes, they did. Good for them. Okay? That uses the product rule. Here's another one. Y is equal to log x squared. Now, just a little bit of a warning here. Just a little while ago, we did the log of something raised to a power. I think it was log of b to the x. And we said the rule was you could bring the x out front. And that was the same as x times the log of b. Okay. That's when the x is raised to a power. This thing is raised to a power. What's the argument of that? It's not when the log is raised to a power. You can't bring the 2 out front. That's not allowed. If the x squared was in here, the log of x squared, then you could bring that out front. But this is log of x squared. Reading it sounds the same, but writing it is different. So what do we do? What kind of function is this? What rule do we use here? Okay, not factor, the power. Oh, actually you're right. You could write this as log x times log x. And that it would be a good way to work the problem. Let's do it your way, and then we'll use the power rule the second way. So let's write this as log x times log x. And now we use the product rule. And what would that give us? And what is the root of log x? What's the root of 1 over x? Okay. Plus log x times 1 over x again. So sure enough, that gives you 2 times log x over x. Okay? This is twice the same thing. All right. Now let's do it using the power rule, which I think is maybe just a tad easier. It's 2 times log x times the derivative of log x. And sure enough, that gives us the same thing. 2 log x over x. Okay. Now, how do they write it? Let's see. Yep, 2 log x over x. I wrote it the same way they did. You could write it 2 over x log x, or 2 times log x over x. What's that? Yeah, it would be like if this was a cosine x. You'd be 2 times cosine x times derivative of cosine x. You chain rule. Okay. So you do 2 times log x times derivative of log x. Again, chain rule. Yeah. That's exactly what you do. Now, like I was saying before, if this was log of x squared, and the x squared was, there weren't any parentheses here, then that just changes to 2 times log x. Okay, and then you take the derivative of that, that'd be 2 over x. That's a different problem. This is the whole log is what's being squared. So you do the power rule for it. So it's very good. Now, yuck. We obtain a useful formula for the derivative of log f of x by applying the chain rule with u is equal to f of x. So we're going to do that next. Let me clear this out of the way so it's related to what we just did, but I'm afraid you'll get it confused. So let's hit it. What we want to do is the derivative of where is it? There, I've lost it. Log of derivative of the log of f of x. Okay? Dx. Okay? It's just basically a chain rule problem, right? What's the derivative of a log function? One over whatever that function is, f of x, right? Derivative of log is that. Second? Of f of x. That's just some function, okay? Now, derivative of a natural log of whatever is 1 over the whatever. That's the derivative of a natural log. Then you got to do the chain rule, derivative of the inside function, which is f prime. So you wind up with f prime of x over f of x. Okay? And they start by saying, and maybe this makes it clearer, they start by saying let u equal f of x, right? Then what you have is d log u because if u is f of x, then we're doing d of log u with respect to x. Okay? Well, that doesn't quite look right, does it? So what we do is we say that's d of log u du times du dx. Yeah, that looks a little better, right? Because if this is u, we want to have this to be the independent variable. But u depends on on x, so you put a du dx here. You can think of this as wiping out the du, so you have d log u over dx, which is what we started with. That's really not what we're doing, but that's good enough to think about. And that is a u. For some reason, my u's are looking a lot like n's, and they're not supposed to. Okay, I noticed that earlier, but I wiped those out. Oh, I hate it when it does that. Get this erased again. My screen holds up pretty well, but then all of a sudden, okay, that's a u. Okay. Well, what's du dx? Oh, wait, let's start here. What's the derivative of log u? Derivative of log x is 1 over x. So the derivative of log u would be 1 over u. And then du dx, that would be d, u is f of x dx. Okay? Well, this is 1 over u, but u is f of x, so it's 1 over f of x times, and what's the derivative of f with respect to x? F prime of x. So that's where you get f prime of x over x. Derivative of the log of a function is derivative of the function over the function. There's no reason for you to have a new formula to memorize. You just do it by the chain rule and you get there, okay? It's nothing earth-shattering. It's just the way you do this. It looks pretty neat, but just do the chain rule and you get it, you know? The derivative of a log of something is 1 over the something, and then times the derivative of the something. I mean, it's just chain rule. Okay. Let's do example 3. I don't think we have an example 3, so I'll clear the slide. And we'll do it here. All right. Okay. Example 3, differentiate this. Y is equal to natural log of x cubed plus 1. What you're looking for is dy dx. What you reckon that's going to be? Okay, it's not a product function. It's a log, it's a chain rule thing. Log of another function. Say that again.
You said log is to the third plus 1.
Right. That's the function that you're taking the log of. But you're taking the derivative of that function, which is the log of that function. Okay. This is a composite function. The composite of log with x cubed plus 1. Okay? So you do the chain rule. Okay? And what's the derivative of log of anything? Derivative of log is 1 over the anything. So in this case, it'd be 1 over x cubed plus 1. And then chain rule tells us then the next step is to take derivative of the anything. And what would that be? No, derivative of this. Okay, let me write it out. Okay. Chain rule says then you do derivative of x cubed plus 1 with respect to x. So you take the derivative of the log, which is 1 over that, times the derivative of what's on the inside. That's chain rule. The derivative of the outside, then times the derivative of the inside. Okay? And that would be what's the derivative of x cubed plus 1? Polynomial function. Derivative of that? 3x squared plus 0, right? Okay? So that would be 3x squared over x cubed plus 1. Okay? Which is exactly this. Derivative of the inside over the inside. Derivative of the inside over the inside. The derivative of log of something is the derivative of something over the something. Okay. But I don't remember that formula. I just do it. You know, derivative of a log is 1 over this, and then chain rule says take the derivative of this. Okay. So there's 3a. 3x squared over x cubed plus 1. Let's do, the b part, the b part, which is y is equal to the log of the square root of sine x. Okay? Now, if that looks a little weird, we probably should, that's a three-way composite function. It's the log of a square root of a sine. Okay? So it's actually a composition of three functions. F of a g of an h. Okay? And you do it the same way. Where would you begin? Y prime would be start with the outside. What's the root of a log? 1 over what's over inside, and that's the square root of sine x. Now, I really don't like writing in sine x, so let me back up a little bit. Let me rewrite this as the log of sine x to the 1/2 power. Which, actually, that's how we should have started. That really is how we should have started. Because if we had started that way, we can avoid this next one, okay? So, that would be 1 over sine x to the 1/2 power, which is exactly what that is, okay? Wait. I don't want to go this route, okay? Because this is a log, you can do it easier than this, okay? Okay. Remember one of the rules of logarithms I just told you about? that if you have a log of something raised to a power, you can just bring the power outside the log. That was one of the properties of logarithms. So let me rewrite this. Let's rewrite our y to be this way. 1/2 the log of sine x. Now we have just a composite function of 2 with a constant in front. So now it's far easier to take the derivative. And what would that be? Can't do anything with 1/2, just carry it along. This will be what? Sine x. Then chain rule tells you derivative with respect to x of sine x, right? Chain rule says do the outer function first, and then the inner function, and then the next inner function, however many it takes. By readjusting and writing an exponential notation, we can eliminate one of those steps. And what's the derivative of sine x? Second? Oh, you should. Nicole knows, don't you? Derivative. What's the derivative of sine x? Cosine x, exactly. Okay, we did that earlier in this section. I don't think you were here that day. Okay? The what? Derivative of cosine? No, the derivative of cosine is negative sine. Okay. Derivative of sine is cosine, but derivative of cosine is negative sine. And here's the way, this is a weird way of remembering that, but if you do the sine x, basically it looks like that, right? Now, its derivative is the slope of the tangent line, okay? Now, on the same graph, pick me another color. Red, okay? Somehow I thought you were going to say that. What does it appear the derivative of that line there, the slope of that tangent line there? That looks awfully close to 1, isn't it? So this would be 1. The derivative of that line would be 1. What's the derivative of this tangent line? Slope is 0. And derivative of this one looks like it's minus 1. Derivative of this one, 0 again. Derivative of this looks like it's 1 again. Derivative of this is 0. Derivative of this is minus 1. Derivative of this, and guess what function you got here? The cosine function. So the derivative of sine is cosine. But let's do it the other way. Derivative of cosine, that would be 0 here, a minus 1 there, a 0 here, a minus 1 here, no, yeah, okay, I'm off. A 0 here, a minus 1 here, a 0 here, and a plus 1 here. Well, what you've done is taken the sign and flipped it over. Minus sine function. Let's do that on a different color. Give me another color. Orange. Say again? Light blue. Okay, we'll do that one. All right, derivative here is 0, right? Derivative here is minus 1. Derivative here is 0 again. Derivative here, it should be cutting through that point there. That would be a 1. Derivative here is 0. Derivative here is minus 1. Derivative here is 0. Derivative here is, derivative here, where it crosses here, is plus 1 again. What do we have here? That's the minus the sine function. See, this flips over there, this flips over there, this flips over there, this flips over there. It's minus sine. So derivative of sine is cosine, and derivative of cosine is equal to minus sine. Okay. Now, we did the other trig functions. They're a lot more complicated, and they're not as easy to see on a graph like this is. But, Nicole, can you remind Rodney what those are? How about derivative of tangent? Again, it's a little more complicated. Secant squared. And derivative of cotangent is minus cosecant squared. Okay? Derivative of secant x, sort of a strange one. It's secant x tangent x. Anyone want to make a guess at what derivative of cosecant x is? Well, look at this. Derivative of the basic functions are positive, of the cofunctions negative. Basic function positive, cofunction negative. Basic function positive. Guess what? Cofunction negative. Okay? And it follows the same pattern. Cosecant x, cotangent x. Those are derivatives of our 6 trig functions. If you go back and listen on YouTube for, which one was that? 2 or 3 lessons ago. We actually derived all those. Okay. Now, let's go back to our problem at hand. We're taking derivative of y, which we have as 1/2. And what is cosine over sine? There is an identity, isn't it? Say again? Cosine over sine. Cotangent. Got it. That should be the answer of 3b. 1/2 cotangent x. Okay? And little hint, anytime you're taking a derivative, if it's got a square root in it, write it as a exponent. Don't try to take derivatives of square roots. They're messy. Take derivative of fractional exponents. They're a little messy, but not nearly as messy. Okay. All right. That does 3a and 3b. Let's see if we can do 4. Okay, I'm going to have to, did you get everything off here you needed? Okay. So let's erase all that ink and do example 4. Calculate this. D by dx of the base 10 log of, well, there it is, of x. Okay. Now, this is going to require us to go back. We didn't do chapter 1. That was a review of pre-calculus. Okay? Now, I think you were in my pre-calculus class, weren't you? I don't think Nicole was. You were in probably, who's, Miss Martin's or somebody else's pre-calculus class? Don't know. Whatever class you were in, you may have gotten to the logs. I don't think we did. Okay, so this is a review here. Whenever you have a log to any base, including natural log, base E of x, here is an identity for you. Now, there's a part of me that wants to scream, where is the A for hum? So I really want to scream that, but don't get too. Log, if you're changing this from log base B to log base A, that's log base A of x over log base A of B. Okay? Now that seems like a strange thing, doesn't it? But you're changing from base B to base A. Okay? And what you do, you take the log base A of x, that's sort of the upper part, and divide it by the log base A of the lower part, which is B. Okay? It's a strange way to look at it, but that is what you got. So what we've got here, well, let's take it one more step. Then log base A of x would then be log base B of x divided by log base, no, sorry. I was thinking, why do you want to do that? I thought that's what they're doing. That's not what they're doing. Let's do this for natural log, okay? So what if our base A is E? So log base B of x would then be log base E of x over log base E of B. Well, log base E is the natural log of x over natural log of B. Okay? So, here's a handier rule. Log base B of x is going to be natural log of x over natural log of B. So this would be the same as d by dx of, instead of writing as log base 10 of x, write it as log ln of x over ln of 10. Right? It's exactly what we're doing there. The log of 10 is just a number. So bring that outside the derivative. 1 over natural log of 10. And then what's the derivative of natural log? Derivative of log x? X. Right? So this would just be simply 1 over natural log of 10, whatever the base is there, times 1 over x. Okay? And they actually write it as 1 over log 10 times x. There's no reason to write it that way, but that's how they do it. All right, I think we just ran out of time. In fact, we went over a little bit, but there's no extra charge. We'll pick up this next time in logarithmic differentiation, okay, which it feels like we've already been doing. But homework exercises here. Do any of the odds 1 through 19. Then do any of the odds. Try these. You may find them a little difficult, but try them. 21, either 21 or 23 or both. Okay? And we'll hold off on the next part until we do a few more. Okay? Now, the good news, bad news situation. The good news is there's no school next week. It's spring break week. The bad news is, oh, you forgot it, right? Really? Okay, the bad news is that means we won't be meeting. Sorry. Get over it.
I see it.
Yeah, you knew I was going to say that, didn't you? Okay.
Yeah.
So we'll see you in a little over a week. Monday week.